Welcome to homework.
Okay, folks, in this video we're going to be talking about this problem. A horizontal power line carries a current of 5,000 amperes from south to north. Earth's magnetic field is directed towards the Earth and inclined downward at 70 degrees to the horizontal. We're going to find the magnitude and direction of the magnetic force on 100 meters of the line due to the Earth's field. Okay, so let me just draw this problem out for you. So if this is the vertical axis is, this is the north, this is the south, and you have a power line that is carrying current. The current goes this way, and you know that the Earth's magnetic field is directed towards the north. Let me use a different color for that. Towards the north, and inclined downward at. That doesn't look like 70 degrees. This looks like 70 degrees. Okay, so this is 70 degrees to the horizontal. Okay, north, south, east, west. So this is the west, this is the east. Okay. So the Earth's magnetic field points this way, and the current points this way. Okay. So how do we find the magnitude of the magnetic force on this current carrying wire? Well, if you remember, if you have a charged particle, dq, and it's moving in a magnetic field, then the force that the particle experiences is going to be given by this formula, dF equals dq v across b. Okay, but in this problem we have more than just a particle. We have, a lot of particles. We have a current carrying wire. We have a lot of particles in this wire, a lot of electrons that are moving. So we're going to do an integral. We're going to sum over all of the particles that are moving, and we can rewrite this velocity as dl dt, and then this cross b. And then we can move this dq and dt together. So dq over dt, but that becomes current. Okay, so this is current, and multiplied by dl cross b. And because I is a constant everywhere along the wire, we're going to pull that I out, and we have dl cross b. And because of the fact that the dl everywhere, this is a straight wire, so dl along the wire is a constant, so we can pull this b out. So we have integral of dl cross b. But what is the integral of dl? It is actually going to be a vector that has a length of the total length of the wire, which is 100 meters. I'm going to call that L. And it has a direction that is the same direction as the current, so I'm going to put a vector sign up here, cross b. Okay, so this is the total force on the current carrying wire. And how do we find the magnitude of this force? Well, the magnitude of it force is just going to be I, magnitude of the current, and then multiplied by the magnitude of the, of the length of the wire, multiplied by the magnitude of the B field, multiplied by sine theta. But we know what theta is. Theta is 70 degrees. Okay, theta is 70 degrees. This is the answer for part A. And the direction of the magnetic force, well, if you do your cross product, this is L. If you do your cross product and you wrap your fingers around L and you curl it towards B, you will get, a vector that points in the west direction, that points into the page, because into the page is west and out of the page is east, so you're going to get a vector. So the f hat is going to be in the west direction. Okay. What? Let me just crank out the numbers for you here. I realize that So what is I? I is 5,000. What is L? L is 100 meters. What is B? B is 60 times 10 to the negative 6. If I remember correctly, I'm not sure. It's either negative 6 or negative 3, but whatever. Let me just say that that this is 60 mu Teslas, because I'm not sure what unit mu is. It's either 10 to the negative 3 or negative 6. Mu Teslas multiplied by sine theta, that is 70 degrees. And that is going to give you 2.82 newtons. Okay? This is the number that I cranked out using my calculator. And I encourage you to verify it in case it's wrong, which it's not. Okay? So this is part A, 2.82 newtons, and the direction of the force is is west. Okay, so this is it for this video. See you in the next video.